All right, so here we have a two-dimensional collision where this zero point 0.4 kilogram mass, which I'm calling M1, comes in with a velocity of 3 meters per second and strikes this other mass, which I'm calling M2, 0.7 kilograms. So M1 comes and hits M2. M2 is initially at rest. And then after the collision, M1 moves up at an angle of 32 degrees from the positive x-axis with a velocity of 1 meter per second. And M2, although it doesn't tell us this in the problem, M2 must move down below the positive x-axis with some unknown angle, which we're going to solve for, with an unknown velocity, with an unknown the magnitude of the velocity we don't have yet. So we basically have two unknowns here. We don't know the magnitude of M2's velocity after the collision, which is this question mark here, and we don't know the angle at which it travels. So this is a two-dimensional collision because after the collision we have motion in the x direction and the y direction. So just to be clear here, obviously what I mean by x is the horizontal, and by y I mean the vertical. So we'll just draw that in. There's our xy. And then another thing that's going to be very important is our sign conventions. To the right is plus, to the left is minus, up is plus, down is minus. Okay, so since this is a collision, the thing that we think about is conservation of momentum. Now, all conservation of momentum, all that means is that the momentum before the collision is equal to the momentum after the collision. And P is momentum, not to be confused with power, because power is also P. Here, P is momentum. So momentum before the collision equals momentum after the collision. But for a two-dimensional situation like this, we have to apply conservation of momentum to the x direction and the y direction separately. We're treating the x and the y separately, just like we did with projectile motion, just like we did when we summed forces. The x direction and the y direction are perpendicular to one another and don't affect each other. So basically, this idea of conservation of momentum is going to be applied to the x direction. So what we're going to say here is momentum x initial equals momentum x final. And then we're going to do the same thing for the y direction. So I'll put this down here. In the y direction, we're going to say momentum y initial is going to be equal to momentum y final. So if we look at our situation, before the collision, all we have is an x momentum because there's no motion in the y direction. M1 comes in with an x velocity, and M2 has no velocity, so therefore no momentum. So our initial x momentum, momentum x initial, is going to be equal, so the way you get momentum is mass times velocity. So 0.4 times 3 gives 1.2 kilogram meter per second. And our initial y momentum is 0. There is no y momentum before the collision. So these values have to be the same down here after the collision. Our momentum x final needs to be 1.2 kilogram meter per second. Momentum y final needs to be 0 kilogram meter per second. So the way this is going to happen, so I'm going to get my red pen out here. So after the collision, M1 is going to have x velocity. So this red arrow is the x component of M1's velocity after the collision, and y velocity. So if there's x velocity, that means that M1 also has x momentum. All momentum is mass times velocity. After the collision, M1 is going to have y momentum because there's y velocity. So this is velocity y, This is velocity x. Now m2 also has x velocity, y velocity. And this y velocity is going to be negative because it points down. So basically, here's what happens. Just like big picture. We have an initial x momentum, which we know to be 1.2. So what has to be true is this x momentum. So the way you get momentum is just mass times velocity. This x momentum plus this x momentum. We have two x momentums after the collision. If you add these two x momentums together, they need to add up to 1.2. Now in the y direction, we had no momentum before the collision. There was no motion in the y. So after the collision, the total momentum has to be 0. And the way that happens is that this positive x momentum that I'm pointing to here must cancel with this negative x momentum. Y momentum. These two y momentums, sorry, I think I might have been saying x there. I meant to say y. These two y momentums after the collision are equal and opposite. They're going to cancel. All right, so let's set up the equations. So this actually is a harder problem for chapter 6, probably the hardest problem, the hardest sort of problem. Okay, so let's start with the x direction. So our initial x momentum, the only x momentum before the collision is m1. So this is going to be m1 v1 initial. That is our starting x momentum. Now, after the collision, we have two x momentums, so we're going to have to use some trig here. So let's start with the x momentum for m1. The x momentum for m1 is going to be m1 multiplied by cosine 32 times v1 final. And we have v1 final. v1 final is 1 meter per second. Plus, so these final momentums are both positive because they both point to the right, plus the x momentum for m2. This is going to be m2 multiplied by cosine theta, right? Cosine theta, we don't have that angle. Cosine theta times v2 final. So we just wrote a very useful equation. All right, now let's go to the y direction. Our initial y momentum is 0. 0 is equal, okay, so now let's go to our final y momentums. We have two y momentums final. So let's start with the y momentum for m1. It's positive because it points up. The velocity for m1 after the collision points upward. So the y momentum for m1 after the collision is going to be m1 sine 32 v1 final. Okay, so this is the y momentum for m1 after the collision. Then we go minus m2. Now it's minus because the y momentum for m2 points down after the collision. And then we want to get the y component of the velocity. So that's going to be sine theta times v2 final. And in my opinion, the hard part is now done. Because what we've done is we've written two equations and we have two unknowns. The two unknowns are, our unknowns are, we have two of them. v2 final is an unknown, and then the angle for v2 final is an unknown. All right, so from here we need to bring in to simplify this down. It's a very common trig identity that is used in physics problems, but what we're going to use here is sine theta over cosine theta is the same as tangent theta. This is going to make the math a lot easier. So I'm going to take this equation here, and basically solve it. I'm not going to show all the substitution of numbers because it'll make the video quite long. But if you simplify this equation here, okay, so we're going to solve this for sine theta V2F, V2 final. And this comes out to be 0.30281 when you plug all the values in. So sine theta V2F equals 0.30281. So verify that on your own, and then we're going to take this equation up here, and we're going to solve this for cosine theta V2F. And when you plug all the numbers into that, you get 1.22969. And then what we do is we divide these two equations. So we have one equation for sine theta V2F, the other equation is cosine theta V2F. We divide the two equations, the V2F drops out. Sine theta over cosine theta is tangent theta. So tangent theta comes out as 0.24625. So therefore, theta is tangent inverse of that, 24625, giving a theta of 13.8338, unrounded, 13.8338 degrees. So that is the angle at which M2 moves after the collision. So now that we know that, we can go back up here and pick either one of these equations. So let's use sine theta V2F. So what we had here was sine theta V2F is equal to 0.30281. So therefore V2F is equal to 0.30281 over sine of theta, and we now know theta is 13.8338 degrees, giving us V2 final as I'll round this off to 1.27 meters per second. So the answer to the first question is M2 after the collision moves with a velocity of 1.27 meter per second at an angle of 13.8 degrees below the positive x-axis. And the reason we know it's below the positive x-axis is our final momentum in the y direction had to be 0. So M1 had a positive y momentum, so M2 must have a negative y momentum because the two y momentums after the collision need to cancel to 0. All right, so the second question in this problem is to find the fraction of the initial kinetic energy that is lost in the collision. All right, so finding the fraction lost of the initial kinetic energy. So I always make the analogy of money. If you have $200 to start with and you lose $50 of your 200, your fraction lost is going to be $50 divided by 200. You lost 0.25, you lost a quarter of your money. So the exact same logic applies with kinetic energy. So what we need to do is find out how much kinetic energy was lost in the collision and then divide that by the initial amount. All right, so we got to calculate a couple things here. We first need to find out what is the kinetic energy before the collision. Only one object has kinetic energy before the collision. That's M1. M2 is just sitting here. So the kinetic energy before the collision is going to be 1/2 M1 V1 initial squared. So that's 1/2 M1 is 0.4. The velocity before the collision of M1 is 3 meters per second. You punch the numbers in and you get 1.8 joules. This is our initial kinetic energy. Now, after the collision, we have two kinetic energies because m1 and m2 are both in motion. So this is going to be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So we punch the numbers in here. So m1 is 0.4. Velocity of m1 after the collision is 1. We square that. M2 is 0.7. And then the velocity of M2 after the collision. Now we want to use the unrounded value. I rounded it off earlier to 1.27, but here we're going to go 1.26642 meter per second squared. All right, so kinetic final, the final kinetic energy comes out as 0.76134. So we have our starting kinetic energy of 1.8. We have our ending kinetic energy of 0.76. So the kinetic energy lost is the difference between those, which happens to be 1.03866. That's how much kinetic energy was lost. Just subtract those two. So the fraction of the initial kinetic energy lost is going to be the kinetic energy lost divided by the kinetic energy initial. So you go 1.03866 divided by the initial amount, which is 1.8, and we get a fraction of 0.577, which is basically 57.7%.